the strain rate, mean strain rate will also be 0 because U1 is constant. Now, so basically we have the flow coming here. It's a turbulent flow. That means basically superimposed on this U1 will be U1 prime, U2 prime and U3 prime. U1 is just the mean velocity. Flow is turbulent, so therefore the turbulent components will be in all the three directions. But now this is the x1 direction, x2 is perpendicular to this one, or x2 is the vertical and x3 is coming out. So now here what happens is the turbulence, when I say turbulence I mean all the mean quantities. They are nearly homogeneous in the x2 and x3 directions. That means if I look at variation of quantities in x2 direction, x3 or x2 direction, the statistical quantities will not change, except maybe very close to the wall where the wall effect is coming. Let's say we are ignoring that. So therefore, in x2 and x3 direction, turbulence is homogeneous. But now, because of this grid will sort of decide the size of turbulence to start with, because if the flow is passing through this, then what you would expect is the eddies which will form, if their size is L as we have taken, that will be of the order of the size of M, the grid spacing, because everything is passing through this. So each of this grid will make some sort of a vertical eddy which will only form the fluctuating part. The mean part is obviously still U1. So those eddies are sort of formed here and the flow goes down. Now what we also assume is that if I am at a particular location, then statistical quantities do not change with time, because mean of U1 is maintained. How is mean of U1 maintained?
So because of the incoming flow.
Yeah, so typically physically how would this be done?
So I mean there will be a constant influx of
Yeah, so how has anyone done experiments? नहीं है? हाँ, तो कैसे create करते हैं experiments में? Either you blow air or at the end you put a fan which sucks in air. So this is physically caused by some sort of a fan or a blower. Either a blower will blow in this flow, or there is a fan which will suck in the air, and so the fan keeps on rotating, and that's how U1 is maintained. So keep in mind that this U1, even for constant U1, some physical source of energy is needed. It is, otherwise the U1 will also die down. Okay? So this is not given in the book, this is not specified anywhere, but we should keep that in mind. So that is how the mean of U1 is calculated, is generated. But then what we want to know is what happens to the turbulence quantities. What happens to kinetic energy, what happens to dissipation, how do they change with x1, because now x1 is the only direction along which these things change. Okay? So that is what we are now trying to see with the help of these equations and with whatever dimension, whatever analysis we have done, can we get to some sort of estimates.
So sorry, can you
Yeah.
explain once more why turbulence is homogeneous in x2 and x3? Is it because there are no mean quantities in those directions?
First is that there is no mean quantity. Also, if we look at x2 and x3 directions, basically overall nothing in a large sense is changing over x2 or x3. Another thing which I discussed, we have this U1 and x1, and I will explain this again, but U1 and x1, one frame of reference is the ground frame of reference, where you see flow moving like this. Another frame of reference I could take where I move with the mean velocity. If I move with the mean velocity, then what I will find is things will change with time. because initially I am here, then I am going down with the mean velocity. So that is my frame of reference. So there, if I measure quantities, as I go downstream, things will change with time. And what we realize here is this x1, role of x1 is similar to that of time if you travel with the mean velocity. So this mean velocity will always come with x1 in terms of this thing, that u1 upon x1 has a time scale, 1 over time scale. So that time scale has the same role as d by dt. So either in that frame, the flow will not be stationary because things are changing with time, but then it will be homogeneous. As you move, you will not see any change in the x1 direction also. Okay?
So are things changing in the x1 direction, like as
Yeah.
we are moving with the particle, because there is because there is birth of turbulence? Like let's say I didn't have the grid to begin with.
No, so even if the grid was not there, things would have changed down in x1 direction. There is flow taking place, there may be viscous effects, there will be some effects. Let's see how do they contribute to. And in fact, we'll not, when we analyze, you will see, we'll not even use the grid. Of course, we know that L will be of the order m, but it could be larger also. See, basically, I think what the grid does is, it makes this turbulence very homogeneous in the x2 and x3. If the grid was not there, then there would be a variation with x2. You could have some sort of eddies like this, so then that homogeneity would not have been there.
So, in the frame of the mean velocity, our flow won't be steady, right?
Our flow won't be steady. You're very right. It will be homogeneous fully. So it is either the d by dt term or u1 d by dx1 term. One of them, and u1 d by dx1 is equal to dt in the changed frame of reference. Very right. Okay. So having understood this physics, let us move to the equations. Yeah. असाइनमेंट का डाउट है कौन सा चैप्टर 2 का?
नहीं, असाइनमेंट ये आपने जो शीट दिया था इसमें।
हाँ हाँ, इसमें क्या कोई प्रॉब्लम हो रही है कुछ?
सर इसमें आपने लिखा है 4 और 1 को माइनस करने पे वो आएगा कंटिन्यूटी इक्वेशन।
हाँ हाँ, नहीं 4 नहीं लिखा था शायद, 4 लिख दिया क्या? नो नो नो, आई डिडंट से दैट. ये subtract 2 from 3 and 1 from 4 to get ui prime. यार ये 1 को 4 से नहीं करना होगा. नहीं, ये कंटिन्यूटी तो अपने आप ही आएगा, इससे 1 से 4 से नहीं आएगा. नहीं वो नहीं that's. अच्छा, anyway, let's move on please. So this was the equation we had. This we had seen. This is, in fact, I've just written the general K equation. This is a valid for everything. So now in today's class, we'll start from simplifying of this equation and move ahead. You should know how to simplify terms like this. Suppose if I give you velocity is equal to u1 plus u2 plus u3. All the three are not zero. And let us say they depend only on x1 or they depend on x1 and x2, not on x3. Then how do you expand this? How do you expand this? And how do you expand this? You should be able to do that. Okay, for different situations, individual expansions you should be able to do. And then maybe I may ask you to show something that use continuity equation to show that this term also becomes zero and things like that.
So you spoke about two frames.
Yeah.
One is me as an observer from the ground, and another is me flowing with the flow.
Flowing with the mean velocity of the flow.
With the mean velocity. Like in one case, my dt term goes away. Like that is equal to 0, and in the other, this one goes away, right? Like
In the so then what I will
u1 del u by del x. But what happens to the RHS?
no, RHS will again d by dxj.
How would that be adjusted?
That would be adjusted. For example, some of these terms, there are no derivatives, they will stay as it is. The only thing is d by dxj. So wherever d by dx1 will come, that will become u by dt or whatever. X is equal to u times dt. So you will get a d by dt here and 1 over mean of u1.
So we have to do it for every derivative term.
नहीं तो वो सीधे d by dt हो जाएगा ना और 1 over u1 आ जाएगा बाहर, nothing else. dx1 will change to that. Okay. Yeah. This is for turbulent kinetic energy, assuming stationary flow.
But it will change for mean kinetic energy.
For
mean kinetic energy, it will change.
which kinetic energy?
Mean kinetic energy.
हाँ, मीन का तो हमने ऑलरेडी डिस्कस कर लिया पूरा. This is only for the turbulent kinetic energy. Mean energy we have already discussed earlier, and now we are coming to turbulence. In this case, there is nothing in the mean equation. U1 is constant, so what you will get is just a constant kinetic energy. So that's why we don't even talk about it. Okay. So this was the last lecture. Now let's move on to today's lecture. The date today is 6. So now when we simplify this equation, so start from I am not writing that again. We start from the last equation of lecture 16, and I think 16 has also been uploaded, is that right? Yes, sir. Okay. We start from the last equation and we simplify. Simplify means d by dx2 of all mean quantities, d by dx3 of all mean quantities, partial by partial t of mean quantities is equal to 0, u1 is equal to constant. So, then we also assume that the viscous term in the transport term is small this we have discussed earlier also, that there is a transport term. In transport term there are 3 terms. There is a d by dxj of ui prime, uj prime, uk prime. There is a pressure transport term and there is a viscous transport term. The viscous term, as we said, if Reynolds number is large, because that scales like c times nu u square upon L square. So that will be small because Reynolds number is large. So therefore that term will be neglected, and based on this what we get is the equation becomes mean of u1 there is no production term here because dui by dxj is 0. Okay? So we get this equation. Now in this equation, when we look at it, now let all the velocity fluctuations, we take the order of magnitude, we call it as urms prime. Okay? And so then what we have is, if we look at mean of u1 dk by dx1, this will be of the order of magnitude mean of u1 upon x1 times u prime RMS square. Pardon? हाँ u1 prime correct, ठीक है. Thank you. So, see what happens is when we take d by dx1, we can't take L as the order of magnitude. Why is that so? Because the flow is going around the x1 direction. So, this x1 direction can go up to infinity depending on the length of your wind tunnel. Whereas L would be some cross dimension related to the height of the wind tunnel. So, therefore, wherever the x1 derivative comes, I have taken it as x1, maybe I can call it as some other L equal to length of the wind tunnel. I will keep it as x1, keeping in mind that in order of estimates x1 will be constant, but of course, if it is in an equation, then we will integrate. Okay. Now, I think last class didn't we show that we had shown it earlier, ui prime p prime, this we showed is of the order of magnitude of or p is equal to rho u square, is of the order of magnitude of rho times RMS cube. And similarly, half of u1, this is also of the order of u prime RMS cube. So, the transport terms are of the order of u prime RMS cube upon x1. Yeah. ये वाला इसमें कुछ भी नहीं है. It's see p is rho u square. मैं पहले rho नीचे लिख रहा था गलती से. I'll erase it. I was making a mistake in my. एक मिनट अभी ठीक कर देता हूँ मैं. So now, when we compare u1 dk by dx1, order of magnitude of this, to the order of magnitude of the transport term, this will be equal to u1 upon urms. Okay, because this is u prime RMS cube upon x1, the other had a capital U times u square. So, the square cuts away, we get it like this. Okay. Now, here we have to use some sort of a information from the experiments to proceed further. And what is found is that in other flows, when we talked of turbulent shear flows, where the flow production terms were not 0, we said that u prime RMS is of the order of the mean velocity. We have used this estimate many times, that the mean velocity and u prime RMS, they are of the same order of magnitude. But in this case, there is no production term. Capital U is just a constant, and in the experiments what you observe is u prime RMS is much less, it's about 10% of mean of u1. It is not too large. So, this is what you find in this experiment, because, and the reason for that is obvious, that there is no production term in the equation. Yeah.
Why is there no production term?
Because the
Viscosity is low.
no, the flow is like this. Now, production term क्या है? U prime V prime dui by dxj. D mean u by dxj. There is mean is constant here. Okay. So, in this flow, it is observed that u prime RMS. Somebody may have an objection to much less than, it is about 10% or so. So let's use it freely, is less. And no, in fact, it's not even 10%. My notes say it's about 0.5%. And this L which we say, so therefore, what an epsilon term, if we look at it, this is of the order of u prime RMS cube upon L. So therefore, the transport term can be neglected, and what we get is mean of u1
above you wrote transport terms to be of the order of u prime RMS cube by x1.
Huh.
So what order is of x1?
So no, x1 is the distance along the downstream this thing. So it will be of the order of the length of the wind tunnel or whatever it is.
Right, because like I'm not able to understand why can we neglect transport terms if we have epsilon of the order u prime RMS cube by L. That means
So
that
now there are
epsilon
two
is a very
terms.
large-
So the first term and so we have a production term, and there is this dissipation term, and there is this middle term. So what we are saying is the middle term is much smaller compared to the first term, and to the left hand side, which was dk by dt term. So if that is much, we neglect that, and so the other term of which we have no idea, so we keep this term. So the equation then, if the second term which we have neglected is much less compared to this, so we have thrown that away, and this is equal to minus epsilon. See, had this term not been there, then we would have had a problem, then both the terms would have had to be very small. Now we do, if epsilon is also very small, then of course all the terms are very small. But here we do not know right now what is epsilon. So we throw that term away and we get it in this way.
Also, how big a small transport term is depends on like the distance.
Yeah, so initially it may not be small, but a few, let's say 10 times after you have gone 10 times this thing from the height of the tunnel or something like that. Yes. So then it will be. In fact, they use instead of height of the tunnel, m is used as the non-dimensional distance here. Dissipation. U cube upon L, which we used. And I have already written that. अब L जो है is some order of the turbulent eddies, large scale eddies, मतलब large और energy containing eddies. तो appreciable, तो we don't know how L goes. L, अभी देखते हैं क्या होता है L का. Let us see, these equations will tell us. Okay, see we have L, which is the turbulent quantity. Let's say it starts off with some eddies, we move slightly away with a constant velocity, and then we observe. So right now we have two things. We don't know how k changes with x1, and the other thing which you asked, how L changes with x1. These are the two things we will try to determine from whatever knowledge we have, just in a very simple way. Only thing we have used here now, one information we have used is u prime RMS is much less than capital U. That information we have used so far. And of course all the stationarity. So finally when you list out, there's a lot of assumptions, but now now if I look at the order of magnitude analysis, what I am going to do is, if epsilon is equal to, then what I get is mean of u1 u prime RMS square upon x1 is equal to u prime, sorry, ठीक कर दो, u prime RMS cube upon L, and from here what I get is u1 upon x1 is of the same order as u prime RMS upon L. If epsilon has to go like u cube upon L, so then what I get is the equations tell me that these two things have to have the same order, which means that the time scale associated with the convective flow has to be the same as the time scale with which an eddy is churning. U prime is the velocity of the eddy, L is the length of the eddy. So the time an eddy takes to revolve is the same time, same velocity with which the flow moves on. Okay, that is what we are getting. So now I can write this equation as, or I can write it in the form u1 upon x1 is equal to c times u prime RMS upon L. Now, still this does not complete. I wanted to find out how kinetic energy, which is the square of u prime RMS, how does it change with x? What do you expect to the kinetic energy? It should decrease. And how does L change? We don't know. So we have a relation with x1 for this ratio, but we don't have a second relation. I need to find a second relation to find how each of these change with x1.
So the mechanism is large eddies to smaller eddies, right?
Yes.
So we are talking about the turbulent kinetic energy. Right?
Yeah.
So as if we take del K by del x1, we know that at some lengths there is no heat dissipation. There is only transfer of kinetic energy. Right?
Yes.
And after that,
Towards the end, finally there will be dissipation.
So here we should expect the kinetic energy to behave in that way, right? So
It should constantly decrease yours.
del K by del x1 should be close to 0 and then it should pick up, right?
Why should it be 0 to start with?
So the K is not changing, right? It's not going into
No,
heat work.
we don't know what is happening to K. As we go down, we are trying to find out how K is changing with x1. See, its turbulence is somehow, the flow has turbulence in it. There are these fluctuations mounted on this u prime. U prime is moving like this. So we want to know what happens. There is no production mechanism. So that is why we expect the turbulence to decay, because there is no production. But otherwise, in what form will it decay? How rapidly will it decay? Is what we are trying to find out.
So here we are, our test material is just a block of air or something.
Yeah, this fluid, high air which is flowing
Is
in.
it infinitesimal or it's a...
No, so we are talking infinitesimal in what sense? We are talking of the air particles which are there, and since it is homogeneous, so actually statistically you can't differentiate between different particles in the wind tunnel.
So this
So-
is taking an arbitrary
And somehow,
size of...
some size arbitrary.
So the problem we are facing here is that we want to investigate how u prime RMS and essentially TKE varies with x1,
Huh.
and we are not sure how
L varies with x1.
which is basically the length scale of the largest
Larger eddies, yeah.
at that x1,
Yeah.
which initially we assume to be the width of the channel
No, initially we assume it to be the width of the, somewhere close to the size of the
of the grid rather.
grid.
But
Now it can increase or decrease. That's what we are trying to find out.
So, can we perhaps change this to like U1 times T like mean
No,
one
so उससे फर्क नहीं पड़ेगा ना, क्योंकि either x1 is your variable or t is a variable. Either you call it u1 upon x1 or call it 1 upon t. They are the same variable.
No, I'm talking about L. Can we write it as? But that would be fair, right? The like writing L as mean u1 times t.
Writing L as mean u1 times t, but which t?
We are not even sure.
We do, so then the t becomes the variable instead of u1. So let's. You can't, matlab, even if you think some velocity scale times t, so what t then? So let's see, let's move ahead from here. So this is one relation we have between u prime RMS and L. Now, to find the second relation, we use so let me first explain the problem. Need to find, I had spoken that how u prime changes with x1 and how L changes with x1. I have simplified, this discussion is given in Lumley, but it is not as simple. So what I have done is, what I am going to do now, in the dimensional analysis part, I have simplified the description from there. I have made it much simpler so that it's easy to tackle. It took me about a day to get to this sort of a simple description. And once it came, then it looked so, this thing. So now in this problem, if we look at, use dimensional analysis. So let us look at our variables. Our variables are, of course, we want to find u prime, how this is changing. So if it is k, then it comes in u prime only, u prime square will be k. Epsilon, it will be u cube upon L. So u prime and L are the two turbulence variables we want to find. Now we want to find how they change with x1. So x1 should be one of the variables, but x1 doesn't come alone, it comes with a mean velocity, because flow in this is being convected with the mean speed. So wherever x1 will come, the mean of u will always go with it. And it is a constant. X1 is an independent because that's what we want to find. But then x1, with it, the mean of u will always go. Because you are talking of a flow which is convecting with this scale. Okay. And which is the other variable, any other physical variable we have? The viscosity, nu. This is in fact. And nu. So these are our four variables. Now, how many independent variables should I choose? 3. जब dimensional analysis की 2. Why? See, u is L by T, this is L, this is L by 1 over T, this is meter square per meter second square, so again L square T. So that means there are two basic variables L and T. So we have to choose two repeating variables. Okay. So I choose two repeating variables. And this is where I played the trick to make it easier. And I choose these variables as u prime and L. I was struggling with how Lumley came to his sort of answers and conclusions, but I found it was very simple. Normally we don't choose them as repeating variables. But because they are 4, so I know I will get only 2 numbers. So I choose u prime, RMS and L as my repeating variables. When you do a dimensional analysis, then you choose 2 of them which contain both L and T, each of them, and then we will non-dimensionalize the other 2. So these are my repeating variables. So I will non-dimensionalize u1 by x1 in terms of these 2, and I will non-dimensionalize nu in terms of these 2. Like the Kolmogorov scale we did. This is a high school physics dimensional analysis, but those ideas, that's what I want to show that, yeah.
We know like the last 2.
Uh,
Won't it be
I know it is, but then I know it is. Normally, I would choose nu and u1 by x1. But then let's proceed ahead. You can choose any two. Because with this, I get to the results which are quoted and which become much easier. That's why it took me a day to come to this. Because obviously I was also like you thinking in choosing these two. हाँ वही कर रहा था मैं, but then I realized कि choosing it other way is what gets me to the result which I need. Yeah. हाँ constant है ना viscosity, ये तो वो वाली turbulent viscosity थोड़ी ना है. Mu upon rho. हाँ. Fluid. हाँ. नहीं turbulent viscosity is a known eddy viscosity, तो basically URMS और L का function है. If I know nu, if I now come to somehow U prime is changing with X and L is changing with X, then I can put an exam question, how is nu t changing with X? And how will that change? U times L. Again, so turbulence का हमें कुछ नहीं पता कोई भी variable. How that is changing with X. That is what we are trying to figure out. Very simple problem, but it's very illustrative. See, it gets out all these thoughts, all these doubts, all these thought processes are what come out when we try to analyze something like that. So, u1 by x1 का क्या बनेगा non-dimensional variable? Of course, one way of doing it is u to the power of a, L to the power of b times u dimension of u1 x1 is equal to L0 m0 t0. But here it is obvious. x1 को ऐसे डिवाइड कर दो, it will be non-dimensional. और u है, L है और nu है, तो इससे क्या बनेगा? Reynolds number. Nu upon UL is a Reynolds number. So straight away you will get Reynolds number. So दोनों dimensional variables. So the final result will be expressed as nu upon u prime RMS L is a function of u1 x1, x1 की जगह हम यहाँ L over u prime RMS. Okay. In dimensional analysis, this is what we do. We started with 4 variables. We chose 2 repeating variables. We will get 2 non-dimensional variables. So one is a function of the other. Actually, I should have done this theory before we did Kohlberg-Grove scales. But that is what happens in dimension. And this I can even write as u prime L upon nu. The function will become inverse of the other thing. We don't know what f is. Dimensional theory will never tell you the functionality. It will just tell you how to reduce the number of variables. So this I can also write it as, so in the other way I write it, or I can write L upon u prime, u1 upon x1, that's the right hand side. This is equal to some function f1 upon of, and I'm more comfortable in Reynolds number, so I invert these, I write it in this way. मतलब see, इसको हम start ऐसे करते हैं. If this was my problem initially, there are 4 variables. The problem. So now any one of them, if I have to express u prime RMS.
Sir, इसमें u prime RMS और L dependent.
अभी dependent नहीं थे. We start from. Why you asking now? Why is one a function of the other? Our problem statement was u prime RMS. Can I simplify this? So first I use dimensional analysis to simplify. Dimensional analysis tells me instead of I will be left with only 2 variables. This is, in fact, this comes from what is called the Buckingham Pi theorem. There's a Buckingham Pi theorem non-dimensional parameters expressed in this function, that some variable 1 is a function of n minus 1 variables, total n variables. Therefore, it can be expressed as n minus r variables will be there, which will be non-dimensional, and pi 1, if I call it group. So pi 1 is a function of n minus r, so this thing minus r. So initially, if there were 3, then I will be left with 3 minus 2, 1. So pi 1 is a function of pi 2. This is the Buckingham pi theorem. A very powerful theorem, holds in all fields, not just turbulence. Solid mechanics, fluid mechanics, any other electromagnetism, anywhere, this will always work. And this is a way which experimentalists use to reduce the number of dimensions. Otherwise, you will keep on doing the experiment for so many variables. But if you group them in non-dimensional variables, you will just have to maybe do one experiment. Okay. Okay. Is this fine? Now, if I compare this statement with the first statement which we had, without dimension. So this is what dimensional analysis gives us. This comes from dimensional analysis. But our equations told us, equations say, so which is the equations are this. The story which I get from the equations is equation A. U1 upon x1 is equal to C times U prime RMS upon L. So equation A tells us, equation A implies, what was it? Let me write down from there. U1 upon x1 is equal to C times. Now I compare these two. This implies, when I compare these two, U1 upon x1. So from here I get U1 upon x1 is equal to U prime upon L times a function of U prime L upon nu. But U1 upon x1 is equal to C times U prime upon L. So this gives me that function of must be a constant. One equation this equation comes from the equation, governing equation. Dimensional analysis tells me U1 upon x1 is equal to U prime upon L times some function of UL upon nu. When I compare these two, it tells me that this function of Reynolds number must be a constant. You sab URMS है, मैं ठीक कर दूँ. Thank you. See, असल में I should put URMS everywhere. हाँ, सब जगह RMS लिख दो. जहाँ पे भी प्राइम है, it's all RMS. So, what this tells us is U prime RMS times L upon nu must be some constant. This is a function of Reynolds is constant, so Reynolds also has to be constant. So U prime L upon nu has to be some constant C1. So this gives you the second relation, how U and L, that U prime multiplied by L must be a constant. The first relation we got was U prime divided by L was U1 upon x1. And the second relation we get is U prime times L must be a constant. So from this, we can get how U prime RMS goes with x1 and how L will go with x1 alone. Because what I'll do is, if I want to find how L goes with x1, I will put, instead of U prime RMS, I will put C1 nu upon L. So that will tell me how L changes with x1. And if I want to find how U prime RMS changes with x1, I will eliminate L. So I will put L is equal to C1 new divided by U prime RMS. And put that in here, that will tell me how U prime RMS changes with x1. Is that fine? Everybody with me? And that is sort of the beauty of a simple analysis like this. Even though we have made many assumptions throughout we made, but then at least we are able to now from here get to the fact that how these quantities will change. Yeah. U prime RMS तो constant order of magnitude के लिए हमने लिया ना यहाँ. RMS तो वैसे भी function नहीं होगा generally. U prime RMS मतलब it could be a function ना, but नहीं, it's a function means अच्छा एक मिनट रुको. Constant ये we are trying to see how this is changing with x1. So in some at a location, if we say it will be constant at one x1 location, at x1 it will, yeah, that is what we are trying to see, because turbulence itself is decaying with x1. That's what we find from here. नहीं, but this is not valid for the Kolmogorov scale ना. Kolmogorov scale में epsilon की जो scaling होगी वो nu u square upon L square से, it will not be u cube upon L. See, this scaling is valid only till you are not in the dissipative range. Okay, this is in the transfer range, you can say. So that means here now, if we continue ahead, let's just एक बार करते फिर I'll answer everything, don't worry. So therefore, one thing which we, from here what we see is, this quantity does not change with x1. Now, of course, this is valid for a few hundred distance, but after some time then this will also not be valid. There will be a more complex description. Then these things are not valid. This is valid for a few up to about 100 downstream lengths below that we find Reynolds number by and large based on this estimate is a constant. Of course, this is not equal to mean of u L by nu here. Mean of u is much bigger than u prime in this case, u prime RMS. So this is, again, maybe I should put RMS here as a constant. So now if we eliminate L, L को तो हमने प्राइम लिखा ही नहीं है. L को तो हमने हर जगह, अच्छा यहाँ प्राइम लिख दिया, सॉरी. इतने सारे प्राइम चल रहे हैं ना, कहीं पे आ गया. ओके. So if we eliminate L, so now we have, this is equation, let's call it C, this is equation D. These are the to eliminate L from C and D. What you will get is U prime RMS square is equal to, is proportional to nu times U1 upon X1. There are some constants, I'm not sure whether it is C times C1 or C divided by C1 or product of C and C1. Because I have sort of goofed up a bit while writing my notes, so I'm not writing the constant, I'm writing it. And what is here, there will be some combination of C and C1, etc., whatever those constants were. Equation C was the same as A. This is equating the two time scales. Mean of U1 upon X1 is equal to C times U prime RMS. A also, yeah, it's the same as A. So maybe I ठीक है, इसको A कर देते हैं, इसको ए एंड डी कर देते हैं, ठीक है, कोई बात नहीं, इट्स द सेम थिंग. So what you find is u prime RMS square goes like 1 over x. So what this will tell you is that kinetic energy and similarly if you work out L in this case turns out to be proportional to root of nu over mean u1. I'm using this proportionality because there will be some constants again, c and c1 times x1 to the power of half. U RMS square. No, K is kinetic energy, so it's Q square.
U prime RMS
Square. K is not. So therefore, if U prime RMS square goes like 1 over x1, K will also go like 1 over x. Constant here. कि बढ़ क्यों रही है लेंथ? But see, when what is going to happen is this, as the flow goes down, the length scale increases, but then in the decaying portion, in the dissipative portion, this doesn't work. Then it will, everything will fall down. But फिर बाद में छोटा हो जाएगा. But in this region, in the few regions downstream, it is, and it's also experimentally verified. See, because L is anyway some quantity which you are trying to see some sort of and even, see, possibly what is happening is, even though there is no production term, but there's a mean velocity going with this. So somewhere that mean velocity is showing its effect on L. That is what is somewhere it is true. That this is what L. Because it gets, maybe it starts off with the, see, I think possibly what happens again is just a conjecture. We start off with this small eddy of the size of the grid, but then it gets us, as you rightly said, that then those eddies get a chance to expand, because the holes, now there is nothing like a grid restricting them to the size of M. So initially they tend to expand, but then once dissipation comes, then everything. So that is possibly what is happening.
in the sense that because according to my edit only increases. But you are saying when dissipation kicks in, it should go down.
So this limit is probably till, I think assignment 1 has one such problem, till REL. Here it is constant, but eventually I think what is going to happen is, as kinetic energy decreases, as U prime goes down, then somewhere you will get a limit where the U cube upon L is equal to C nu U square over L square. When you equate these two, this will give you some sort of a limit. L? Obviously, even K equation won't hold up in those limits once you are in the dissipation range. So these equations, this is just for, and this we have obtained, as you realize, from the equations and all. It was a very heuristic, very thumb-waving arguments, you can say, got us to this. But when we actually check this, it is within about 20% of the, to 30% of the results. This number, I think I have it somewhere in my notes. Actually, if we say that this K, which we got as, if we write K is proportional to x to the power of minus n, experiments show that n varies from 1.1 to 1.3. We got this number as 1. If I write k is equal to x to the power of minus n, experiments show that n varies from 1.1 to 1.3. So now I leave it for you to figure out how will epsilon go like x. I'm sure you can all work out from this. How does dissipation change with x? And then, of course, one thing one can do is also, if you realize the equation we had, if I write things in terms of the frame moving with the mean velocity, then the equation becomes dk by dt is equal to minus epsilon. Okay? And if k I choose, then epsilon will go like x to the power of minus of n plus 1. Just you substitute the value, just differentiate it, you will get how epsilon goes. And then that should be the same as what you get otherwise. So basically, kinetic energy is following a what we call a power law for decay as it goes downstream. Okay? अभी नहीं मैं कह रहा I'll ask you to figure this out somewhere. अच्छा आज सब लोग हैं तो is there anyone who is not present today? कितने 16 लोग हैं मतलब आज 13 है तो कौन कौन नहीं है? एक बेटा अटेंडेंस लिस्ट तो मैंने कई बार कहा मुझे दे दिया करो, मैं देख लूँ नाम भी बुला लूँ, मुझे पता तो लगे ना कौन कौन है. आई डोंट इवन नो. अभिजीत, ओके, अभी किसी की क्लास तो नहीं है ना? 2-4 मिनट में खत्म कर, पढ़ा नहीं रहा मैं. और अर्नब